Okay, so in this video I'll be explaining the atomic and ionic radius. So how it works is that, let me draw the general trend for atomic radius first. Okay, generally this is the radius, okay, but it's in nanometers. Okay, so generally for atomic it's relatively easy. This axis is just the sodium to chlorine. Okay, so this radius is in nanometers, and how it works is that generally from sodium to chloride, it will go down. The reason why this, by the way, this for period 3, yeah, okay, why I don't write argon is because argon is all the way up here. Okay, so the reason why argon is all the way up here is even higher than the sodium even, okay, is because argon is actually is calculated by Van der Waals radius. And what is this radius? So argon is an noble gas, so basically it is not chemically bonded. Okay, no covalent bond, no ionic bond, no metallic bond, it's just one argon like that. So essentially this is a nucleus, and how they calculate the radius is they take this and divide by 2. So this is the radius that they're calculating, which is this distance. But for example, chlorine, right, is actually bonded together. So there's the keyword, overlapping of orbitals. Such that how they find the radius, they take the nuclear and then they cut this into 2 and like that. So naturally, okay, maybe let me make this bigger a little. Naturally, this is actually much bigger. Sorry, okay. Naturally, okay, this distance here is much smaller, right? So essentially, all the chemicals from here to here, from sodium to chlorine, is actually has a smaller atomic radius. So this is how they calculate the atomic radius. They find the radius of this molecule, then they divide. They basically, what they do is that they will find this distance. Okay, they find this distance. So it is not the full distance. The full distance will be covered in blue. This is the actual distance. But what scientists or chemists calculate is the one in red, the arrows in red, which is this one. Okay, so this is how they calculate. So usually we do not draw argon. Okay, so generally the atomic radius actually goes downhill, or the downwards trend, it decreases from sodium to chlorine. So let me just give you a little rundown of why it decreases. First of all, with the from sodium to chlorine, it actually increase in proton number. So we know that this nuclear charge actually increases. But successive electrons, then I'll explain why successive electrons are added to the same, keyword is same, outermost valence electron shell. Okay, so hence the shielding effect is approximately the same. It's about the same, so I will just put this for the same. Okay, so what happens is that the net attraction, I'll explain again what is net attraction, between the nucleus and valence electron shell is the same, or remains relatively constant. Hence the effective nuclear charge actually increases. Because how do you calculate effective nuclear charge? Effective nuclear charge is equals to the what? The nuclear charge minus the shielding effects. Okay, so that's how you calculate effective nuclear charge. Because if the shielding effect, what is shielding effect? Basically, for example, I have like that, right? I have this atom. Okay, for example, what happens is that the nucleus to the valence electron shell, which is the outermost electron shell, actually has a weaker attraction to it, because there is a layer. Where's the layer? There's a layer here. There's a layer of electron shell in between, so it's like a barrier that blocks it. Okay, that's why the shielding effect occurs. But let's say if I only have one electron shell, there is no shielding effect. Okay, so means it has a stronger attraction to it. In other words, it's much closer to it. Okay, it has no less. Yes, it experiences. Usually we just say shielding effect. Sometimes books also use the word screening, so you can also say screening effect, but our syllabus will use shielding because that's what is indicated in the syllabus document. So that's how you solve it. So that's how you explain. So successive electrons added to the same outermost valence electron shell. Let's take a look. This is sodium, right? For example, this is sodium. Okay, sodium has one valence electron. Okay, then next is magnesium. It has two valence electrons. Okay, can you understand? Can you see now? 2 valence electrons. So now I'm just using the secondary school method of drawing, okay? Next will be aluminium. It has 3 valence electrons. Yes, 3. So you see what I mean by successive electrons? It means the next electrons are added to the same outermost valence electron shell. You see? You see how this is added to the outermost valence electron shell? It's the same. Keyword is same, same outermost outermost valence electron shell. So that's how it works. So shielding effect, as I explained just now, okay? So the net attraction between the nucleus, which is the center, and the outside will be much stronger. Wait, sorry. This net attraction will increase. Why? Because the effective nuclear charge increases. Why effective nuclear charge increase? Because nuclear charge increase, but shielding effect remains the same. So overall, there will be an increase. Okay, so that's how it works. So now I'm gonna explain ionic radius. I want to explain ionic radius. How it works is that we have this, then we rise. So this will be your. Okay, this will be your. This is actually your atomic. This is your ionic. Okay, this is actually silicon. Okay, so I'll say sodium plus or silicon 4 plus. Okay, I'm not gonna draw the ones between. Okay, so from sodium, okay, let me explain why. First of all, I'm gonna explain the K ion trend first. K ion is actually smaller than atoms. Why? The reason being, K ion, first of all, they have one less electron shell. Okay, so this is, for example, let's say this is sodium. Okay, sodium has 2 electron shell. Okay, okay, maybe the inside shell is filled. Okay, so this is sodium. Sodium ion, to make an ion, you have to put the plus outside, and then how? You have to remove an electron, right? When you remove the electron, the outermost electron shell has no electrons. Like the inner one actually has electrons. Okay, the outermost has no electrons already. So does the shell still exist? It doesn't, so no more shell. So what happens? Compared to its atom, which will look like that, sodium atom, this actually has one less electron shell. Okay, one less electron shell. So that's why the K ion is smaller than the atom. Okay, smaller than atom. And then still got one more explanation. We talk about the electron shell, but we also never talk about the shielding effect. Okay, shielding effect. Okay, anyways, from the center, from the nucleus here, okay, to here, there's a barrier here that shields the attraction. So therefore, this to the valence electron shell is much weaker. Okay, whereas sodium actually only has 1 valence electron. Okay, so from the center to the nucleus is much stronger. You see, there's no barrier, or there's fewer barriers from the outside most to the inside. Okay, so this is the reason why the one less electron shell and shielding effect. That's why K ion is smaller than atom. Now what about N ion? N ion bigger than atom. Why is it bigger than atom? First of all, let's draw a normal N ion. For example, this is chlorine. Okay, if I want to make it an N ion, what do I do? For example, this is ES7. ES7. Okay, if I want to make it an N ion, I add another electron. Okay, so again, many people will say that it actually will become it will remain the same size because the number of electron shell remains the same, right? But yes, that explanation it's not gonna work. It's okay. The reason being, it becomes bigger because this is the normal atom. When I add this, it becomes an anion. So there is actually additional repulsion. What's the additional repulsion? Because this is negative, right? Okay, this nucleus is positive. The nucleus are always positive because nucleus contain proton and neutron. Neutron is neutral, so means it has no charge. Okay, proton has 1 charge, so this nucleus is positive. With this electron, it will actually repel such that this electron shell will actually kind of like grow lah. So instead of being this size, it will become maybe like this size, slightly bigger, because it will repel. Okay, it will repel. Okay, so when it repels, and then it's actually further away from the nucleus, right? So now instead of like that, wait, let me see again. Sorry. So instead of being like that, okay. Wait, what the hell? It's not working. actually becomes slightly bigger. Okay, slightly bigger means what? The distance between the nucleus and the shell actually increase. Distance between the nucleus and the shell increase. So means there is weaker attraction, right? So this is same number of electron shell, but further distance from nucleus. Why? Because of additional repulsion. What's repulsion? From the nucleus to here, it will become bigger. Okay. I use from the nucleus because that's easier to understand. But in actual fact, generally the repulsion does not occur there because we know nucleus is positive, right? And then this is negative, right? So it will actually form electrostatic force of attraction. What happens is because maybe there's another electron shell inside. Then this electron, because inside here, this electron, right, it will repel, slightly repel. Okay. Okay. So generally it's because there's another electron shell inside, so there's additional repulsion due to the addition of negatively charged electron. Okay. Okay, so that's about it. But now we're gonna explain the graph. Okay, explain the trend now. Why is it from sodium to silicon it actually decreases? Why is it that the ionic, and then from phosphorus maybe to chlorine it actually increases? It actually decreases. So generally because from here to here it is actually what? The proton number. Wait, sorry, I'm not writing here. Proton number 3. Now I'm explaining for the downward trend between the elements. Between elements, not within the element. Within element, just now I talked already. Between the atoms and cation, and between atoms and anion, just within the element. Now it's between the elements, proton number increase again, nuclear charge actually increases. Same explanation as atomic. But what happens is that you're not talking about electrons, successive electrons added to the same outermost electron shell. Instead, we talk about sodium to silicon. Okay, same thing for the anions. Okay, sodium to silicon, they have the same electron shell, same number of electron shell, and same number of electrons. Okay, the same number of electrons. So basically, in other words, they are isoelectronic. What does this mean? It basically just means that this anion, or particle in general, possess the same number of electrons as the other particle. The isoelectronic. So what happens is that the shielding effect remains the same. But what happens is doesn't remain the same is the proton number. So proton number was proton increase. Okay, and then nuclear charge increase. So essentially the net attraction will actually increase between the nucleus and the valence electron shell. Okay, then therefore it will become smaller and smaller. So just like that. So it's the same explanation as this. There's a reason why it's going down. Okay, now we compare between cation versus anion. Okay, first of all, cation versus anion. Cation has one less electron shell. Okay, one more electron shell. So essentially cation has one more electron shell, anion has one more electron shell than cation. Not because anion added electron shell, it's because cation lost an electron shell. Okay, so you can talk about the distance. Okay, talk about the distance from nucleus. You talk about the shielding effects. Okay, then essentially you will come to a conclusion that cation has more than anion. Okay, you also have to write that anion has more protons than cations. But this does not explain why, because increased proton number means what? You're increasing the effective nuclear charge, right? So essentially, theoretically, based on this explanation, anion should be smaller. Than cation. But we know it's not true because cation has more than anion. Cation has is smaller than anion, not the other way around. Okay, so that's how we explain for atomic radius and ionic radius. Just for J1's period 3 periodic table. Okay.